Hello, everybody. Welcome back to EM378 SI Online. Hope it's been a stellar week for you so far. We got a problem here that we're going to work through, but don't forget we got WebEx meetings that happen every Monday, Tuesday, and Thursday at 6, 6, and 5. This is Iowa time. So make sure you show up if you have questions, want to see more problems worked through, or got any content like that. And we got an exam a week from the day that this video is posted. So the exam number 3 should be on 4-21, which is a week from today if you're watching this the day it comes out. So make sure we're catching up on studying for that. I'll have a review session that I'm going to figure out what I'm going to do with that. Depends on if Dr. Schaefer has anything planned. But I'll send out an announcement for that, and then, yeah, I'll let you know what that looks like when we get there. Let's get into this problem. So this is going to be similar to the one that we had yesterday, or in the last session, I should say, that where we're dealing with the Bernoulli equation and losses in pipes. All right, so here we go. Let's start by writing out, well, let me read the problem first. Water at 10 degrees Celsius is pumped from a lake shown in the figure below. Flow rate is 0.01 meters cubed per second, and we want to know what the maximum length of the inlet pipe L can be without causing cavitation. So using our Bernoulli equation, which looks like this, V2 over gamma plus V2 squared. That was almost a gamma. There we go. 2G plus Z2, then plus HL. And remember, HL, when we're working with pipes, or this loss that we're working with, is the friction factor times the length over diameter plus sigma KL, both of those multiplied by V squared over 2G. And the sigma KL depends on connections, inlets, outlets, that sort of thing. So let's get started. So we have to pick our points for the Bernoulli equation, and as per usual, if we see a large tank open in the atmosphere, we're going to pick the surface of that for a point because that makes everything a lot easier. And the other question that we want to ask is, where's our second point going to go? We're tempted to say right here at the end of this pipe here, but the problem is we don't want to have to deal with this pump here, because that's going to add another factor here, right? It'd be plus HP, which is the pump head, and that'd be another term that we don't want to have to deal with. And so what we can do instead is say our point 2 is just before the pipe, right? And that'll give us this same elevation that we're given here, while also having a velocity from inside the pipe. And we want to know stuff about what's going on in the pipe, right? We don't want cavitation to occur. And remember that cavitation occurs when pressure is below the vaporization pressure, which for water is 1.228 kilopascals. That's absolute pressure, not gauge pressure. All right, so we have our points, and we know what we're looking for, which is this L value here. So let's get started. So we have point 1 and point 2. We'll need their pressures, velocities, and elevations. So the pressure at 1, it's 0 gauge pressure, which is 101 kilopascals absolute pressure. Right, we're putting this in absolute pressure because our pressure at point 2 has to be like that right there. All right, so maybe that's going to focus a little better. All right, there we go. Hopefully we can read that. And for velocity, we know that the velocity here, since this is a large tank, is going to be 0. And velocity at 2, we don't know, but using our flow rate, we can find that fairly easily. That's not any better. Wait. Make sure you guys can read this while I'm working. All right. So And now we're going to work with elevations. We're given elevations of 650 and 653. Or you could say this is 0 and this is 3. Same difference, but as long as you have them written out. All right, so we have our little chart. And then solving for this velocity using our continuity equation, 0.001, or sorry, that should be 0.011. There we go. That's our Q. And then our A, pi over 4 times the diameter of our pipe, which is given as 0.07 meters squared. And then we get 2.86 meters per second. Alrighty. Oh, this document. Oh. Alright, that's a lot better. Okay, cool. So, next thing that we're going to do is we're going to plug all of our values in, plug our velocity. Well, we're not going to do that. Actually, we're going to solve for, before we plug everything in, let's solve for this friction factor and our sigma KL, and then we'll have everything that we need. So to solve for a friction factor, we need to know if it's laminar or turbulent. We do that by finding our Reynolds number. VD over nu, 2.86 times diameter of 0.07 divided by nu. For water, that's 1.307 times 10 to the negative 6th. We get 1.53 times 10 to the 5th. And this is greater than 4,000, so we have turbulent flow, which means we're going to use a Moody chart or the Colebrook and Holland equations, but just for practice with the chart, I would suggest doing that in case you don't have a calculator that can do that for you. So if we're going to use the Moody chart, we're going to need epsilon over d. Let's see. Yeah, we're given an epsilon. We're not given or relative roughness. We're not given what the pipe is, but we have the number, so we don't have to bother with that. Notice it's in millimeters, so we're going to say 0.08 and convert our diameter into millimeters. And we'll get our epsilon over d, 0.00114. And using our Reynolds number and epsilon over d, we check the Moody chart, and we get a friction factor of 0.0216. Alrighty. And for sigma KL, we look at this and we ask ourselves, all right, where are potential losses? And that's at entrances, exits, and connections in between. We don't have any connections, so there's no KL, there's no loss coefficients from the in-between. At the exit, it's just an open exit. There's no losses there. But at our entrance, we have a pipe is inside the water, right? So we're going to lose a little bit as things are flowing in. There's a loss coefficient that happens there, which would be given to you, and that is 0.8. There aren't any others, so sigma KL is just 0.8. Now we have all of our numbers that we can plug back into Bernoulli's equation and then solve. So point 1, pressure velocity, elevation. Then point 2, 1.1228 times 10 to the third. Sorry, can't forget that. 9.8 times 10 to the third. This is also 10 to the third because it's kilopascals, right? Right? No, that's not 10 times 10 to the third. Just kidding. All right. And then 653 for the elevation. And then for these, I factored v squared over 2g out of this term and then out of HL as well, just to make things look a little bit cleaner. So we have 2.86 squared over 2 times 9.8. and then 1 plus 0.0216. Running out of room a little bit here. We'll figure it out. 206 times our L, which we're looking for, 0.07. And then sigma KL 0.8. Aha, nailed it. All right. If you're working on an exam and you start running out of room, go ahead and just make things a little bit nicer. So anyway, you can subtract stuff over, divide it out, multiply it out, whatever you need to. But the value you're going to get is that L, focus, L is equal to 50.0 meters. So, yeah. All right. Before we finish out, I want to revisit why I selected point 2 as up here. I mentioned earlier that we need a point in the pipe and we don't have to deal with the pump. But the other thing about point 2 is this is also where the lowest pressure is going to be, is at this highest elevation, and where there hasn't been any pump action yet. So also, it's the only point that we know stuff about, right? We're given this elevation here. We don't know exactly what the elevation is between here and here. But yeah, so we chose point 2 because that's where the lowest pressure is going to be, and we want to prevent cavitation. So we chose an L for a maximum L there, and it'll be a good time. So this, I wouldn't be surprised if this is a type of question you see on the exam, because it involves the Bernoulli equation. It involves using the Moody chart, all things that we've been using so far. All right. So at our next session, meet me on WebEx. We'll talk about predicting exam questions, what to expect on the exam, and yeah, if you have any questions, feel free to bring them there. You can also contact me through the SI website. And if you know anybody else in the class, let them know that this YouTube channel is up. I'm trying to help out as many of you guys as possible. Make sure you guys are still getting the SI content that's helpful for you. And we will have an exam review. TBD what that's going to look like, though. I'll send out an announcement for that. All right. With that, have a good day, everybody. I will see you guys in WebEx.